Thank you for giving me the opportunity to speak here. I'm Sepehr Nezami, a postdoc at Caltech, and I'm going to talk about quantum gravity in the lab and size finding, which is based on two papers with archive numbers listed here and with Adam Brown, Hrant Gharibyan, Stefan Leichenauer, Henry Lin, Grant Salton, Lenny Susskind, Brian Swingle, and Michael Walter as my collaborators. Let me start with some general motivation and start with a lesson from holography. Holography has taught us to think of gravity and spacetime as dual descriptions of non-gravitational, but often complex and chaotic quantum systems. In other words, you can have in your lab a non-gravitational system that when you look at the system differently, with a set of different variables, different parameters, it does have a dual description in terms of a theory of quantum gravity. And our goal here is to understand or further the understanding of the emergence of this gravitational dual picture with the tools of quantum information theory and design experiments in the non-gravitational picture that are sensitive to the gravity dual. So you can have in your lab a non-gravitational quantum system, like, but non-gravitational is just like every device that you can imagine you have in your lab. And it does something. It simulates a quantum system, or it just itself is a complex quantum system. And in some cases, this quantum system has a gravitational dual. And you want to observe phenomena that are characteristic to the gravitational dual and otherwise might look quite surprising or unexpected in the non-gravitational picture. For, in our case, we are choosing a phenomena called traversable wormholes in the gravitational picture, and we are going to study the non-gravitational dual of that could potentially be implemented in the lab. And the nice thing that we observe is that something in the gravitational dual, a phenomenon which is very simple and characteristic of gravitational system, which is simply the free falling of particles, has a surprisingly complex and interesting dual in the non-gravitational picture, which is to some extent unexpected if you don't know about the existence of gravitational picture. And this dual of a particle free falling is nothing but a kind of a complex form of quantum teleportation, as we will see. So we are proposing experiments to see this particular type of holographic teleportation. And to do that, we find a circuit, quantum circuit, which is dual to this wormhole and study that. So to start, I'm going to talk about outline of our work. So first, I'm going to talk about a little bit about holographic duality. It's not really essential for understanding the technical parts of this talk, but it is really good to have a general understanding of what the big picture is. And then I'm going to talk about two results. So we will see that the circuit that is dual to this gravitational traversable wormhole can teleport in two different regimes. The same circuit teleports in two regimes. One of them is quite unexpected from gravity, and the other regime of teleportation is something that you expect from gravity, and it's teleportation through a gravitational wormhole. So this is going to be our results. And here I've listed a number of relevant resources for this talk. So let me start with the holographic part. And as I said, in holographic duality, we have a non-gravitational system and a gravitational system. Here we choose a non-gravitational system to be a zero-dimensional quantum system containing 2 points. Each point can have many fermions or qubits, but they are not. There are for our purposes they are zero-dimensional. The whole non-gravitational system is 0 + 1 dimension because you still have the time direction. And so these are these red lines in this slide. And the gravitational dual is nothing but the sheet of space-time connecting these two boundaries. So you would have a dual description of what happens on these two lines in terms of a theory of quantum gravity and this sheet of space-time. And this picture that I'm drawing here is a Penrose diagram, which is slightly misleading. because it's finite, but the real system that we have is infinite. So the distance between these two boundaries when going through this gravitational picture is infinite, and the time also goes from minus infinity to plus infinity. But this is according to the rules of Penrose diagram, it's a highly distorted picture, and we have squeezed everything so it can comfortably fit in one slide. But the actual geometry and picture is something infinite. But as we distorted everything, we kept one thing fixed, and that's the fact that the light travels at 45-degree angles. So if you have a line that travels with if you have a path or a line that travels with the angle more than 45-degree, it would be space-like. It could be something that travels with a speed of less than the speed of light. And if you have a particle moving with angle less than 45-degree, it would be time-like, and it's basically impossible to have such particles. And in particular, you would not be able to, and any signal that you release from the left boundary would end up in the upper part of the system, which is a singularity, which is where when your signal basically dies because it hits the black hole. But it's a singularity of the wormhole. And the important fact is that you cannot normally in this wormhole setup send a signal from lower boundary from the left boundary to the right boundary, because any signal that goes from left to right has to travel with an angle less than 45-degree, and that is impossible because that would be superluminal signaling. And so this is the reason that wormholes are usually not traversable. You cannot send signals from one side of the wormhole to the other side of the wormhole, unlike interstellar. But it was Gao, Jefferson, Wall introduced a notion of traversable wormhole, and they have a simple and elegant trick. So what they do is that on the boundary side, they act by a simple coupling that acts on both boundaries at time equal to 0. This is a very weak coupling that touches many qubits, but very, very lightly. And the net effect of this coupling, as they observe in the bulk, is sending something called the negative energy shockwave. We are not going to talk about what a negative energy shockwave is, but the net effect is that when you release a particle that's going to its demise in the singularity at the top, it will grab the signal to the right-hand side and releases it again so it reaches the other boundary. So in some sense, this coupling does something to the bulk geometry that makes the wormhole traversable. And you would see that this line looks broken, but this is an artifact of the Penrose diagram, as artifact of our drawing. And when you release a particle in this particular geometry, it feels nothing. It just free falls from the lower left to upper right. So you can actually send signals from this side of the diagram to the other side of the diagram if you using the gravitational background, using the gravitational spacetime, using the quantum spacetime between these two boundaries. But now at this point, I'm going to switch from gravitational picture to the more quantum information picture, and I'm going to introduce this quantum circuit. As I'm going to explain, this circuit is really the non-gravitational dual of this gravitational spacetime, and this gravitational teleportation picture. I can just start by introducing how these two pictures map to each other. So as I said, the boundary has only 2 points. These 2 points, I'm going to separate them into 2 subsystems. A thick subsystem, which is this line of this circuit. The time goes upwards, of course, like this picture. The thick line contains most of the qubits or fermions, and the thin line contains just 1 or 2, or generically a small number of fermions. And this thin line is where we put our signal on. It's where we act on when in the geometric picture. When in a gravitational or geometric picture, when we act by this quantum channel or operation. And So this is a left boundary or left system. The other two lines, the combination of them is the right boundary. Again, it has a thick subsystem, which has most of the fermions, and a thin subsystem. And then you act by this operation in negative time. So this epsilon channel is nothing but this is acting on the left boundary in negative time. So you have to time evolve it backward by conjugation by this time evolution operators and act here. And then you have this coupling, which, as I said, is a simple coupling. It is normalized by n, when n is a number of qubits in the thick line, z left, z right coupling. So it just acts on the first qubit on the left and first qubit on the right by a zz operation, and does the same for all other n qubits. And it normalizes it by n. And then there is a coupling prefactor g. But keep in mind that when n is large, when you have many qubits, this is a really mild operation on each one of the qubits. And then you receive the signal on some positive time. So you time evolve it forward and you get the signal out on this thin qubit. So now if you look at this picture, at this point, we can totally forget about the gravitational picture. So if you look at this quantum circuit, it is fairly surprising that you get any signal back, because you act by this operation. You insert your signal on this qubit and time evolves forward, upward, of course. And then you scramble the signal with this time evolution. So the signal is totally, seemingly lost here. It's highly scrambled. And then what you do next is acting by a very soft coupling. So you just like touch them by tiny operation, touch many of qubits by tiny operation. And then again, you time evolve it further. So it seems like you are scrambling even further. But somehow surprisingly, you get state psi out. So the question is that we know that such teleportation should happen because particles free fall in gravity. But now the question is that how we can understand it how to understand this circuit using the normal quantum information language, and in what regimes and when it teleports. Oh, I forgot to mention that the initial state here is this thermophile double state, which is nothing but a purification of the thermal state. That's the standard initial state for all wormholes. So, as I said, the circuit works in two different regimes. One regime is unexpected from gravity. It has low capacity and it works with high temperature. The temperature is the temperature of this thermophile double. It's easier to understand from the quantum information perspective. The second regime of teleportation is easier to understand from the quantum gravity setup. And that is the one through the wormhole, and it requires low temperature, and it has higher capacity. And as we explained, we need to use the language of size, operator size, to understand it in the framework of quantum information theory. So let me start the first regime. So the first regime works best when t left, TL, the time evolution on the left, is equal to t equal to right, t time evolution on the right, and they're both very large. And it works best for large temperatures, meaning that when the thermophile double is simply a collection of bell pairs. This is all very pleasant experimentally. And then we can also consider this signal injection by simply injecting a new qubit. So by erasing this qubit and injecting your favorite psi in state into this circuit. And you can see that for chaotic Hamiltonians, and even when you have a two design, you can get a perfect, when you have a time evolution, which is the two design, you can get a perfect signal out. For example, this is when you have a Hamiltonian, which is totally random, is all entries are random, and you can do analytic calculation. And you see that at early times, of course, it doesn't teleport because the Hamiltonian does nothing and the signal gets traced out. But after a while, you get a stronger and stronger signal and you get your qubit out perfectly. But the fun fact is that this type of scenario can teleport only one qubit. Even if the qubit, if you had a Q-treat, you would have not gotten any, you would lose fidelity. And if you have 2 or more qubits, you will exponentially lose fidelity. And that's interesting. And as I said, you can have a time evolution, which is just like total random unitary, and it still works for that. And you can actually send more than 1 qubits if you, instead of a random unitary, use long spin chains, which are chaotic or randomizing enough. And given that you inject your qubits with a large enough distance in this chain. So there are many different regimes that you study this type of systems in the paper, and I refer you to the paper. And I'm not going to explain in details how it works because it just requires some circuit manipulations and playing with the circuit. But I'm just going to give you a very big picture, and so please believe me about the circuit equalities. So to just explain that why this protocol works and why you can send only 1 qubit, you can see that the circuit at infinite temperature is equivalent to what you see on the right. So when the time evolution is this unitary U, and this is more or less a simple circuit, and it has two qubit inputs, and you have 2 qubit outputs. So this is your input, this is output. This is equivalent to this one. It's not immediate to see, but you can do that. You can derive the circuit from the right one. And then you can see that when you compute the average over this unitary, say for over a 2 design, you can see that the circuit implements this particular operation, which is nothing but changing the sign of the phase of one state in your system. So it does nothing to all the states in this combined Hilbert space, but changing the sign of the 5+, and one of the Bell pairs, the main Bell pair state. So you can see that this operation is not really changing the phase of one state. It's not really powerful enough to teleport many qubits, but it happens to be strong enough to teleport just 1 qubit. And that is how this system works. So now we can talk about the experimental realization, and we can talk about what operations we need to perform in order to see this type of teleportation. And the number one operation is preparing the bell pair, the initial state at infinite temperature. We need to be able to do forward and backward time evolution because you have both types of time evolution when you inject the operator. You need to be able to do the weak, kind of a weak left-right coupling, this ZZ coupling. And you also need to be able to do local controls such as deleting or inserting qubits and doing local measurements. And you can, for example, see here with we have many different proposals for doing this type of experiments. And one proposal is using this kicked Ising model. I'm not going to talk about the details of this model, but you can see that even with n equal to 7 qubits on each side, you can see significant result for like 0.4 fidelity. You can send signals with simple systems and simple models. Now I'm going to talk about the second regime of teleportation, the one that is really interesting from the perspective of gravity, from the perspective of quantum gravity, and the one that corresponds to a particle free falling through a traversable wormhole in the holographic dual picture. Before talking about details of this type of teleportation, I need to talk about the operator size distribution for 1 or 2 slides. I will come back to the teleportation protocol right after that. So what is the size distribution? You start with an operator O, which could be in a small 1 or 2 qubit Pauli operator, for example, and you time evolve it at time t by conjugation with this Hamiltonian time evolution, and then you expand the resulting operator in the multi-qubit Pauli basis with the coefficients Cp. So we know that multi-qubit Pauli operators are a basis for the space of all operators in the Hilbert space, and you can always expand any operator in this spaces. And the size of a Pauli operator P is a number of x, y, or z's appearing in P. And it's easy to see that this operator is Hermitian, therefore all these Cp coefficients are real. And now we can see that the operator size grows with time. At time equal to 0, the operator is small, it's just like a 1 or 2 qubit Pauli operator. And therefore, most of non-zero CPs correspond to the CP, the coefficients that have very small size. So this is at time equal to 1. Most of the non-zero Pauli operators have very small size. But as you increase the time, this operator base, the operator gets larger and larger, and its support contains larger and larger Pauli operators. So you see that as I increase the time, the support of this Pauli basis and the support of this Pauli basis goes to the multi-qubit Pauli operators with more and more number of X, Y, and Z's in their expansion. And as I said before, this CP coefficient, so this is the size of the Pauli operators. This is a plot of the CP coefficient. This is the size of P, and this is the imaginary part of CP, which, as I said, is 0 because all these operators are because all these coefficients are real, and the real part, just the support of the real part, always grows with time. So this is a normal size distribution that is defined everywhere. And now I'm going to talk about the thermal operator size distribution. And instead of expanding the operator of O of t, now I expand the operator of O of t multiplied by rho beta to the power of 1/2, when rho beta is the thermal density matrix. I don't have time to talk about the motivation of this definition and why we even call this operator a thermal operator, but we will see the relevance in our work pretty soon in the next slide. So now I expand this thermal operator in the Pauli basis, and you see that the CP coefficients are now complex because this operator is non-Hermitian. And the real interesting phenomena is that as you increase beta from 0 to larger beta, or equivalent to as you lower temperature from infinite temperature, these CP coefficients, when they become complex in a very coherent way. They obtain a phase which is linear in their size, and a phenomena that we should call size winding occurs. So this is the same plot, but as you increase beta for thermal operations. And we expect this phenomenon of size winding to happen for chaotic systems and those that have a holographic dual. And we expect it to happen only near the scrambling time. We have observed that in the SYK model, and we argue that this phenomena should happen if you have a successful holographic teleportation. So now let me talk about the connection between the size winding, this phenomena that we observed in the last slide, to the teleportation through the wormhole. So start with this picture that you have this space-time and you have an operator inserted in the lower left. You can do this and you have an state at time equal to 0 on these two boundaries. And then you can do the normal state to operator mapping. This is just the one that you take the state and you put the entries in a matrix, because now you have a state that's living on the tensor product of the same Hilbert space, and Hilbert space tensor product itself. Then you can rearrange the numbers in the state into a matrix. Yeah, so it's not really crucial for this purpose to really talk about the details, but what I want to send along is that this particular setup, when you have operator injected in the lower left, corresponds corresponds to OT times rho beta to the power of 1/2. You can look at the paper for more details. But now the operator inserted in the upper right, when the target should go, so corresponds to the rho beta to the power of 1/2 times OT. So I agree that I know that the mapping between this picture and this operator is a little bit mysterious, but it's not really a hard thing to derive. But the main fact is that the place that the operator inserted, you insert the signal on the lower left in this gravitational diagram correspond to this order of the operators. And when you hope to get it after the action of the coupling, when the signal is supposed to be received, corresponds to the multiplication of same operators with a different order. And now look at the drawing of the size distribution of this particular operator, and this corresponds to the rho OT times rho beta to the power of 1/2 corresponds to the size distribution as winding clockwise. But now, if you look at the other operator, rho beta to the power of 1/2 times O of t, which corresponds to the received signal, the signal that has been sent on the upper right, it is nothing but the Hermitian conjugate of this operator. So all the coefficients obtained, all the CP coefficients that we talked about in the last slide will be complex conjugated. So you will have basically the same type of size distribution, but winding counterclockwise. So the direction of winding is the opposite. But now to understand how this traversable wormhole works, you need to look at the action of the coupling and notice that the coupling, what it does is effectively it just adds the linear phase to the size distribution, a phase proportional to g and the value of the size. So the net effect of this coupling is nothing but taking this size distribution of the left column, which corresponds to operator injection in the lower left, unwinds this size distribution, unwinds it to the opposite direction. In this way, it maps this size distribution of clockwise winding to counterclockwise winding, and correspondingly it maps the operator injected in the lower left to upper right. And in this way, it sends a signal through the traversable wormhole. So we identify the size winding as a dual mechanism on the boundary for traversable teleportation through the traversable wormhole. So to summarize our paper, our work, we started with the traversable wormhole setup, and we talked about the phenomena of a particle falling through a traversable wormhole, and we looked at this equivalent description in the non-gravitational system that you can potentially implement in the lab. This non-gravitational dual system is a quantum circuit that we made, and we saw that from the quantum information point of view, it teleports in two regimes. The first regime that's easier to implement experimentally is simpler, and it works at late time, it has lower capacity, and it is really much less gravitational. It does not immediately correspond to something falling in a wormhole. And the second regime that works for a narrow window of time and works only for low temperature and uses size winding is the teleportation through the wormhole. And we argued that size winding in strong form should exist in systems with gravitational dual, but really the important message I want to send is that approximate versions of size winding even exist in Hamiltonians, such as the totally random Hamiltonians, this GeV ensemble. So although the systems don't have a nice gravitational dual in any form, the same physics that makes the signal going through the wormhole to some extent, although not perfectly, to some extent even exists in this kind of system. So that would open up a venue for investigation in systems that don't have a perfect holographic dual but share the same physics as traversable wormhole. And our work, I didn't have time to talk about this, but our work is immediately related to size momentum conjecture, which basically says that the size distribution on the boundary is really dual to the momentum wave function of particle falling in the bulk. And open questions are the following. So just two of the open questions are the following. We need a better understanding of the size winding, hopefully a non-gravitational understanding of size winding phenomena, because it can be explained in very simple forms. It's just like a size distribution and operator growth. And lastly, we need to make theories and just like move to other experiments for low temperature thermophile double experiments, and the ones that are actually correspond to a particle falling through a traversable wormhole. With that, I finish my talk. Thank you.